See, we have studied about simple harmonic motion, where you had when the particle is displaced from equilibrium position, you have a restoring force acting on that particle. Here in damped harmonic motion, when a particle is displaced from equilibrium position, alright, when a particle is displaced from equilibrium position, then apart from restoring force acting on it, you have one more forces. Apart forces acting on the particle are forces acting on the particle are, one is restoring force, which is given by minus kx. Second is you have a damping force. Damping force is taken as proportional to velocity and opposite to it. This is bv or b dx by dt. This is the damping force. See, if you have seen a pendulum, right? If you take the pendulum on the right hand side and leave it, it start oscillating. But you find that over a period of time, the amplitude of oscillation keep on falling. And finally the amplitude becomes zero. So you say it's because of damping. It's because of damping force. Apart from restoring force, there is a damping force acting on the body, which is constantly dissipating the kinetic energy into heat. So this is dissipative in nature. This damping force is dissipative in nature. It constantly dissipates kinetic energy into heat. So the mechanical energy is getting converted into a heat. Mechanical energy continuously gets converted into heat, and the amplitude of oscillation falls. The amplitude of oscillation is falling. Energy is getting converted into heat. So the net force acting on the particle is, or this can be written as mass into acceleration, which is md square x by dt square, is minus kx bv, or we can write v as dx by dt, or this can be written as b by m dx by dt, or k by m 0. Right. Let's try to get x as a function of time. Let b by m is taken as 2r. Here b is the damping constant and r is called damping coefficient. K by m is omega naught square. So your differential equation becomes, let's try to find out how displacement varies with time. The equation becomes d square 2rd becomes 0, or d is minus 2r 4r this is this. Now you have three cases depending on the amount of damping force. Let's take case 1, where r is, say, greater than omega naught. That's the case of heavy damping. Here your x will be e to the power minus RT C1 sine plus C2 cos T. Sorry, this is wrong. See, I'm very sorry. This is C1, it's not sine cos, which is C1 e to the power plus C2 T, right? So you find that it is non-oscillatory, it's a non-periodic function. So motion is non-oscillatory. The particle once displaced from equilibrium position will come back to equilibrium position after a long period of time. Particle once displaced from equilibrium position comes to its equilibrium position after a long time and remain at rest thereafter. So it is non-oscillatory. This is also called, the motion is also called dead beat. Dead beat. Now I'll go for the second case. Case 2. Let's go for the case 2. In case 2, this is the case when see, you have the heavy damping. Suppose you have a container like this filled with water, something like this, and inside you have a pendulum, and I bring it to one side and leave it. What do you expect? This bob will come to its equilibrium position after some time and then remain at rest. You can expect the oscillation to take place in water also if the mass is not very heavy. So can't expect the oscillation to continue in water. It is non-oscillative. Particle once displaced from to equilibrium position, it will come back. Right. Now let me consider case 2. Case 2 is when R is omega naught. This is called critical damping. In case of critical damping, you have the equal roots. This is C1 plus C2t e to the power minus RT. So again, this is non-oscillatory. Again, this is non-oscillatory. Particle once displaced from equilibrium position will come back to equilibrium position after a period of time which will be a bit less than compared to the heavy damping. I write it over here. Particle once displaced from equilibrium position will come back to its position after a period of time which is small compared to that of heavy damping and remain at rest thereafter. Right. Now, so this is also non-oscillatory. This is called critical damping. This is also non-oscillatory. Now let's move to next case, that is light damping, where damping coefficient is small compared to omega naught. Damping coefficient is small compared to omega naught. That's called critical damping. In this case, x will be e to the power minus RT. Let's we write in this case this as plus minus I. So this will be minus R omega dash, where omega dash is called damped frequency. We call it damped frequency. This is C2 cos omega dash t. So this is equal to and this is C1 upon C2 cos omega dash t. So let C1 square C2 square is A, and tan delta is C2 upon C1. So this is A E minus RT sin omega dash T cos delta sin delta. All this is this. So this is X. So you find that the amplitude is decaying over here. The decay in amplitude is because of the K is getting converted. The mechanical energy is getting converted into heat. Mechanical energy is getting converted. Mechanical energy is proportional to A square. So if mechanical energy is getting dissipated because of the work done by damping force, which is negative, work done by damping force converts a part of K into heat. So that's why the amplitude is falling. The amplitude falls here. You're right. The amplitude of damped oscillation is falling. It's falling exponentially. We define here one quantity called mean lifetime. What is mean lifetime? It's time interval during which the amplitude decays to 1 by E of its initial value is called mean lifetime. This is called mean lifetime. Now I'll show you how the amplitude of the damped harmonic oscillation decays. Before that, let me give you the value of this mean half lifetime. Suppose T is the mean lifetime, so this will decay to 1 by E of its initial value. So that is A E minus 1, or time is 1 by R. This is mean lifetime. 1 by R is mean lifetime, right? I'll draw the graph showing how the positions are varying, how X is varying with time. So I can draw it. This is how X varies with time. This is how, in case of light damping. In case of heavy damping, it will be like, this. This is the case of heavy damping. The particle, once displaced, come back to equilibrium position, but it takes large time. See, this is the time taken by the particle to come back to equilibrium position. In case of critical damping, it will be less. In case of critical damping, it will come back as small time. This will be the time taken in case of critical damping, right? So this is the case of critical damping. This is the case of critical damping, it is less. And in case of light damping, is still smaller, and light damping is oscillatory also, but amplitude is decaying. It's oscillatory, but amplitude is decaying. In case of light damping, the time period defined as 2 pi by omega dash, which is 2 pi omega naught square minus R square. This is about light damping.